Okay, so for six, we saw a homework, a lecture question. Oh, sorry, a question in the lecture notes about this. So it's cube root up top and square root down below. So what you probably would want to do, they did something kind of creative with this whole x business. I think I probably would have done this. And if you did this, I think that's totally fine. Um, I would have done probably the cube root of 1 plus h plus 1, both top and bottom. That way I can at least cancel something, right? So if you do that, did you do that, Laura? Kind of. Okay, good. I appreciate your honesty. Thank you. Well, if I do this, right? Well, if I multiply cube root with a cube root, what do I get? I get that expression raised to what power? Two, right? So I'm going to write as 1 plus h to the 2/3 power minus 1 over all this junk, right? Square root of 1 plus h minus 1 cube root of 1 plus h plus 1. And then what I'm going to, but see, if I still plug in 0, I'm going to have a problem, right? So then what I think I'll wind up doing, kind of take a leap of faith here. Um, I think this will work. I think it will work. Yeah, I think we're gonna be okay. We're gonna be okay. Trust me.
Like, why did it change from X approaching 0 to X approaching?
So I'm not doing that. I'm doing my own thing. So I'll give you an alternative. Because it's similar to what I did. I did something like this in the notes. Now, I'm doing a conjugate again for the top. You could do a conjugate for the bottom, but I chose to do it for the top. Would it matter? I don't think it would. But here's the deal. After I do this, so you guys see what I'm doing as a second step? I'm finding another conjugate, right? What happens here if I multiply this out? It's 1 plus h to what power? Yeah, minus 1. Now here's the beauty about what I did. Well, actually, is it beautiful? I don't know. Hold on. Maybe. I thought we were gonna be okay. Give me a sec. 1/2. Dude, hold on. If I multiply, I was thinking if I multiply the bottom two, that would have worked out, but I don't think that is going to be okay. So you have 1/3, you have 1/2. Uh, hold on, guys. I may have made this worse. Maybe I should look at the answer key.
So you need to root one.
Well, I'm trying to do the bottom of my head, and I don't like what I'm seeing right now. I mean, if you do 1/2 plus 1/3, that's going to be 3/6 plus 2/6. That's 5/6. I don't like that. You could, or hold on, 2/3 and 1/2. That's 3/6 plus 4/7/6. No. Okay. I am gonna look at the answer key now. My apologies. Okay, I was trying to get creative. Okay, so let's look at the answer key then. So x equals that. So where do they come up with that? Oh, okay, I think I see what they're doing here. Okay. Yeah, here's what you have to yeah, this is not super easy. Why do let x squared equal the cube root of 1 plus h? That becomes x squared minus 1. And if you do for the bottom, it becomes this. Why is that advantageous? That's because you can actually factor out x minus 1 in each case. I think the top's pretty easy. The bottom, I think we talked about this. I'm not sure if Mr. Van covered this with you guys, but there's this formula for difference of cubes, which looks like this. And then those go away. And then you could bring the x back in the mix. And of course, x equals this. And I think that's why that happened there. You replace cube root of 1 plus h with x squared. Yeah, the reason why that makes sense is because if that's true, then that's true. And if you cube it, you do get square root of 1 plus h. These are all consistent. Yeah, it's kind of a very creative problem-solving process. Yeah. Um, I'm not asked this on the quiz. I don't think I'll necessarily ask this on our test. So maybe it's just more just for curiosity how you approach this. So yeah, this is a little crazy. It's not quite, I mean, it's definitely if I want to challenge in BC, then great. But anyhow, I'm not yet. So you intentionally set so you want something that you can factor. That's really hard to see how that factor is going to go. So that's why we put x squared there. If you let x squared equal this, so maybe you start with that, right? Let x squared equal that top. Then if you square root, x equals the 6th root of 1 plus h. Because what happens when you square root x squared? You raise it to the 1/2 power. What happens when you have 1 plus h raised to the 1/3 power, and then raise that to the 1/2 power? That comes to the 1/6 power. So that's how you get x equals the 6th root of 1 plus h. Then if you cube x equals the 6th root of 1 plus h, if you cube it, you get x cubed equals square root of 1 plus h, which enables you to do the substitution in the bottom. So yeah, the more I think about it, I think this is probably the proper way to do it, but let's just not worry about it. 7 might be a better one to worry about because I am gonna ask them like 7 on our quiz. How are you guys with 7? Is that okay? You find the LCD? We're okay with that? Okay. For 4, 4 you were given a hint. Um, hopefully that was a-okay. Hopefully that was fine with the substitution and canceling. Thought 4 is a fair question. 6, yeah, seems a little crazy. Any other questions? Stuff you want to talk about? 8 I like a lot. Conjugates. Actually, 8 wasn't even involved college. You just plug in. Which one, sorry? What number is that? Okay. Yeah, okay. Yep. Yes, correct. Right, which one's which? Yeah, think of x plus absolute of x plus 9 as a graph, right? So that's y equals absolute of x minus 9. So it takes on two forms, the right half and the left half. The right half is a positive slope. And if actually it is x minus 9. So you're going to do x minus 9 when x is larger than 9, right? The other one is going to be its negative counterpart, which is negative x plus 9. If you work that out, you should get 2x minus 9. That's when x is less than 9. And then the equal part could go to either inequality. It doesn't really matter. It's up to you. You choose. But that's how I would approach it once you get to absolute of x minus 9, which is true because you're square rooting a square, right? So that's like square root of x squared is not x, it's absolute of x. So that's how you want to look at it. Is that okay? It's up to you. You choose what you got. You got to put it somewhere. Depends. It might be on the bottom. It might be undefined. Yeah, it's undefined for 16. That's why. It's undefined for 15. So you wouldn't want to have it there. It's undefined for 14. You wouldn't want it there either. Yeah, the other ones are all undefined, looks like. Yeah, I thought all these were pretty safe problems. 6, ugh. That was a little intense. I thought my way was going to work. And maybe I need to rethink it. Maybe I could find a different way. They don't do it differently and got it. Yeah. I'm going to try ChatGPT it. No. All right. Okay. We're good. Everywhere else, we're good. Okay, cool. So for limits, just so you know, on Schoology, great. Now my computer's slowing down. So Schoology. Let's see here. So I do provide you guys some practice for our quiz on Thursday. Here we go. Yeah, so it's a Delta math assignment. I'll also put an extra limits worksheet if you guys want to practice. It'll be 4 questions, some time limit. Yeah, you can see here I have like limits of rational functions, radical expressions, complex fractions, trig limits. These are going to be, I think, pretty straightforward, but just good practice. And I also put a worksheet too, so you have plenty of practice for the quiz coming up. So okay, let's go to the notes. We're going to do 3 pages of notes. We're going to talk about continuity today and like the formal way of proving continuity. We're going to classify things that are not continuous. We're going to work on something that involves continuity and kind of explore a little more. And yeah, that's what we're doing today. So let's start with page 13. All right. So the existence of a limit depends on the idea of continuity. In order to understand this, but we need to understand what it means for a function to be continuous at a point. So continuous over an interval, you may have learned about this already. So there's an intuitive definition for a function that's continuous over an interval as one that can be sketched with the pencil from the paper from the beginning to the end of the interval, or for those who are a little more high tech, for listening to your stylus off the screen. So determine whether the function's graph is continuous on the closed interval from A to B. If it's not continuous in the closed interval from A to B, then name the type of discontinuity at that specific point. Okay. So basically you're looking for something that's not necessarily nice and smooth. It could have like, sharp corners, but just something where there's no break in the graph. So essentially that's what we want. You want no break in the graph. You want to be continuous over an interval. So let's look at the first graph. Is there any break there? Nope, so that's continuous. How about the next one? Yeah, so it's not continuous at x equals c. And we call this either a point discontinuity or a removable discontinuity. Either one's fine. You can say however you want. And it kind of makes sense because you're removing a point, right? So either one's fine. Um, these two here. No, no. And same thing here as well. What's the reason for, what, you guys remember what I called this one? The third one? Jump, yeah, because it jumps off the graph. And yes, it is a vertical asymptote for the fourth one, but there's a more formal term. Infinite. Infinite is continuity because there's an infinite notation, infinite nature to it. And then how about the last one? Remember what we called that one? Oscillating, yes, correct. Oscillating is continuity. We don't really consider oscillating too much, but the other four we do. It's gonna be like this. Um, actually, one sec. I think it's is this X or X? No. It was I think it was that. I don't remember. I don't remember how it looked, but yeah, but that's the sound for that one. Okay, well, let's keep moving. So here are the conditions for continuity. So if you think about it, let's just focus on 2, 3, 4 on the previous page. The second, third, and fourth graphs were not continuous. Did the limits exist? Maybe, maybe not.
Mhm.
Did f of c equaled the actual limit value? Like for a second one, f of c is what? Like 3 points something? But what's the limit as x approaches c? Maybe 2 points in, right? So the limit didn't equal f of c. So here's what has to happen to have continuity. You have to have three conditions. This is like actually probably one of the most important things we do in this unit about continuity. First of all, f of c has to exist. Because if you don't have a point there, forget about it, right? That's a problem. F of c exists. So in order for there to be an interior point x equals c, and this is in the interval from a to b, closed interval from a to b. So an interior point c, in order for that to happen, f of c exists. Also the limit as x approaches c of fx exists. So it means that the LHL is equal to RHL. Lastly, f of c has to equal that limit. And there's going to be a formality that I actually do want you guys to kind of state these things. You can't be lazy about it. So I'll show you some examples in a moment. And when defining continuity at a left or right endpoint, you use the three conditions above, but then you just focus on the one's appropriate one-side limit. So for example, are we continuous at x equals 0 from the right side of root x? Well, yeah, we use the appropriate one-side limit, just so you know, because it is a left endpoint. So you want to make sure you're aware of that. So you could say that. Does the limit exist as x approaches 0 for root x? No. But as x approaches 0 from the right side, it does. So you could say it's continuous at root x as long as you're using the appropriate one-side limit for the second condition. and of course the third condition. So these are the conditions for continuity.
So you would be allowed to say it's continuous?
Yeah, you would. Yeah, for root x at x. And actually, I don't think you even need that when you're asked that question. I think just you write that superscript when you start writing your limit notation.
You have to specify.
Right.
So for the function that has a jump distance continuity or something else, that's continuous from that point onward.
Mm. It won't be because the left hand limit will equal the right hand limit. It's a jump. Like for ex actually, let's talk about this really quickly here.
So at that point is
Yeah. So here, F of C exists. Actually, this is good discussion. Let's do this first before we do the example. F of C exists, and the limit but F of C does not equal that.
Well, couldn't you say it's continuous for everything C above or above C?
What do you mean, above C?
Like how you just said with the root when you just said.
Oh, right, right. Yeah, for root x, sure, it's continuous for root x at. Wait, what's your question actually? I'm not sure what the question is.
Do you never say it for one of these? Like at root x above, you say it's continuous past x equals 0.
Yeah, but this is not the one I just did is not continuous at x equals c though. Is that? I'm confused.
Okay.
What's your question?
Like the point, no.
Are you trying to compare to root x?
Yeah.
Okay, so for root x, it's continuous on its entire domain from 0 to infinity. And of course, it's continuous at x equals 0 because you could use the appropriate one-side limit. But for here, it's not. We're only focused on C, by the way. I don't care about anywhere else.
Okay.
I'm just focused on C. So maybe you're overthinking it, perhaps. Now, so that's what's happening here. So basically, conditions 1 and 2 pass. Condition 3 fails. Now for a third one, FC exists, right? It's like 1 point something. But the limit as x approaches C of f of x, does that exist? No, D&E. Once a condition fails, just stop. You don't need to go any further. Condition 1 passes. Condition 2 fails. Don't bother with condition 3. Because it's not really worth it, right? Here, well, here's what's happening. More specifically, FC could exist. I can actually put a dot here if you want to. As a piecewise function. You totally can. However, what's the key thing here? The limits are going to infinity. The limit as x approaches C plus of f of x, and the limit as x approaches C minus. Positive infinity or negative infinity. Positive infinity or negative infinity. Even though they're both the same sign, it's still going to be infinite discontinuity because of infinite nature. Here, very important, LHL does not equal to RHL. And they're finite limits. meaning they're going to source some number on each side. So that's how you distinguish among those three types of discontinuities. Those are only three I care about: jump, point, or code removal, I guess, and infinite. Um, Let me show you a question I could ask on a test, which I'm totally going to ask. I'm going to tell you right now. I'm going to ask this question, change it up, but I like this question. Lucy had a question.
Oh yeah, like
Hmm?
how come f of c could exist? Because isn't there like an asymptote at c?
You can make a piecewise function.
What,
You do whatever you want.
how that work?
F of x equals 1 over x minus 2 when x is not equal to, and it equals like, say, 3 when x equals 2. You do whatever you want.
Oh,
Yeah, it's up to you. Piecewise functions, you have total freedom. Let me show you a question I've done in the past in AP Calculus. This is in the AB version of the course. Vertical asymptotes. Piecewise function. You do whatever you want. Just exclude the x value and just say, oh, at x equals 2, it's this y value. 100% you can do that. Yeah, I know. It's kind of weird. You can. It can or may not. If it doesn't exist, forget about it. Then I mean, in the case I just showed you right now, it didn't exist. So that's the reason why it's not continuous. However, to call it infinite discontinuity, what really matters is the limit itself, the left-hand and right-hand limits are going towards positive or negative infinity. That's the real reason why. Let me show you a question I've done in the past that involves this. Here we go. Like my favorite question. But I'll produce these for you guys. So you have this practice. Our test is not until the beginning of February. Um, oh yeah, now we're talking. Here we go. I remember I did something kind of like this, I think, in the beginning of the semester or beginning of the school year. So you notice I have all these conditions like, oh, the limit x approaches -4 is this, the limit x approaches -4 is that, and all these other things, and you have to generate a graph that satisfies all these conditions. And then afterwards, you have to tell me what the discontinuity is probably what discontinuity is happening here. Without us drawing it, look at this question, part B. State the type of discontinuity for f at x equals -4 and the reason for your choice. Well, if you think about it, what's happening here? Jump, there you go. Now you know. What if I had this? What would be now? Good. Okay, what if I had this? And I threw that condition in. Then what? Yeah. Or what if I exclude it from my domain? Still a point because it's been removed. So yeah. So these are all options you could have. Okay, so that's how I'm going to assess this stuff, just so you know. Okay, let's keep moving. Now that we've had that greater discussion, let's do the example. We'll do one more page and we're done. Okay, so you're asked to graph this. That's easy to graph. Where's it start? Yeah, -5 to infinity. So -5 comma 1. It's an endpoint, right? If I plug in -4, I should get 2. If I plug in 4, I should get 4. If I plug in -1, I should get 3. Okay. So for part B, I'm gonna cue this up for you guys. Okay, first off, does f of -1 exist? What is it? Okay, check. The limit as x approaches -1, is it the same from both left and right sides? And what is it? Check. Does f of -1, which is 3, equal limit as x approaches -1 of f of x? Check. There you go. That's how you verify it. So you have to go through the 3 conditions, state what they are, and state the last, and then look at the last condition. That's all you gotta do. So for C, we do the same thing. And because it's a left endpoint, we're going to use the appropriate one-sided limit. And look at the box here. Remember, the appropriate one-sided limit is okay for endpoint of a domain. It's kind of a formality more than anything else. It's not that hard. Like here, what's f of -5? What's the limit as I approach -5 from the right side? Does f of -5 equal the appropriate one-side limit? Yeah, check, check, check. So yes, yes, yes. So you're going to be doing that for homework. It's kind of mundane, but we need this for derivatives. This concept of continuity is absolutely crucial for differentiability. The ability to find a derivative. We need this. The formality just seems kind of like, why are we doing this? Wait a few weeks. You'll see why. It'll make sense. For now, we just have to just kind of accept this formality. It's kind of boring. It's actually my least favorite thing to do with this class, but it's important. Are there any points of discontinuity? No. Is a continuous function? Yes. The reason why, you focus on the domain. I mean, of course, there's nothing going on to the left of -5. So is it continuous at -6? Well, of course not. But what you have to consider is its domain. Anywhere in its domain where any breaks in the graph? No. So yes, it's a continuous function then. The answer is yes. So questions on that one so far? Oh, okay. Let's keep moving. So it says right here, a function is continuous if it's continuous at every point in its domain. And of course, if you're defining a certain interval, of course, look at that interval. So we'll do examples 10, 11, and 12, then we're all done. You guys should know it's up here. Hopefully know it's up. Now, we do specify an interval. Is this continuous on the interval from all real numbers? No. That's because there's an infinite discontinuity at x equals 0. Well, what's a domain, though?
Everything excluding 0.
Yeah, right. So it's a continuous function, yes. Because x equals 0 is not part of domain. So it begs the question then, well, what the heck is not is not continuous? Piecewise functions, if you so choose them to be not continuous in its domain, or in this case, a greatest integer function, which looks like this. By the way, it's kind of tricky. It kind of looks like this here. kind of a weird looking bracket. And everybody's expressed it int or floor, whatever. So is this continuous on all real numbers? No. The domain is all real numbers. So no, that's because you have removable, oh, sorry, jump. My bad. Jump, discontinuities. For all, excuse me, for all integers values of x. Okay. So that's happened for example 11. So yeah, it's just kind of going, using the formal definitions of continuity. All real numbers part of the domain, but clearly you have all these breaks. Okay, questions on 10 or 11. All right. And then lastly, for example 12. You guys can start homework, and I'll show the homework, just what to expect. You guys should be pretty comfortable graphing this. So 1, comma 2, is it included? No, it's not included, right? Okay, good. I go to the left or to the right? So it kind of looks like that, like a fish hook or an anchor. Well, the next one in green, or really light green. If you put 1 into that, what do you get? Okay. Actually, am I really following the instructions? Not really. That's okay. I don't pay attention to directions. I'm the kind of person who's built something and I figure I messed up. I don't anyway, like IKEA furniture. Um, but here's the deal. How can you prove it? You do your conditions. F of 1, the limit as x approaches 1, and compare. What's F of 1, guys? According, yeah, obviously go to the bottom one. Check. The left-hand limit. So we kind of need to do for this one here, you need to evaluate both left and right-hand limits. So you kind of need to show that work. But it's pretty obvious. The left-hand limit's 2, 1 squared, which is 2. The right-hand limit's 5, 1 minus 3, which is also 2. I know I'm getting lazy. I should write the limit notation. Um, oh, wait. I'm sorry. F1's not 3. I'm losing my mind. What is it? 2. That's 2. So lastly, does 2 equal 2? Check. So all in checkout. Limit does exist. If it didn't, it'd be a jump or you're done, right? What if you have 5x minus 2, but kept 2x squared? Then you have a jump and you're done. Or what if the limit did exist, but you threw in a third condition that, oh, well, when x equals 1 specifically, it's this value. Like we could have had this, for example. You totally could see this. Well, if I snuck in a third condition in the middle, what if that was just greater than? And I snuck in a 4 when x equals 1. Then when that happens, f1 does exist. The limit exists, but does f1 equal the limit? No. Then the third condition fails. That is a point or removal discontinuity. So those are the things we have to look out for. So we are going to do a lot of piecewise functions in this class. So that's one way of looking at it. Okay. I think that's enough for today. I don't want to do much more than that. You still got 30. Lovely. 32. That's awesome. Look at that. You guys can. I know there's a lot of. I don't care about football anymore. But anyhow, you use your time to do other stuff in life. I don't know. Um, but homework number 6 is what you're gonna do. So like it starts, I think, on page 3, and I will specify in Schoology what to do. Um, you can see some problems here that are going on. Homework number 6. There's some stuff, some limit stuff, and then there's some continuity stuff here, and there's some stuff on the following page. Of course, yeah. And yeah, that's it. So you guys get a head start, and I'm gonna record the quiz grids and pan it back to you guys. I'll stop the recording.